Okay, so let's talk about ionic activity. And to be honest with you, all the equilibrium constant expressions that we have written earlier is not the real equation. Okay, so those are just idealized version. If you could still recall, if we have this reaction A and equilibrium with B, we usually write the equilibrium expression as the concentration of B raised to B over the concentration of A raised to A. However, this is an idealized version. So this is just an idealized version, assuming that there are no ionic effects. Okay, however, in the previous videos, we found out that you have to account for ionic effects. Okay, so hence we have to correct our way of writing the equilibrium constants into activities. So we're going to replace our concentrations in terms of activities. So activities is defined as the concentration of your substance times its gamma. So this is the concentration, this is the ionic uh, activity coefficient, and this is the ionic activity. So what we're doing previously is that we are actually neglecting this gamma term. So we're neglecting the ionic activity coefficient, hence we only use the concentration part in our equilibrium constants. However, since we know that ions have effect on the equilibrium constant, we have to account for them using ionic activities. That means the correct form, the equilibrium expression, let's say we have this substance A plus B in equilibrium with C and D. The correct way of writing the equilibrium expression for this one should not be in terms of the concentration but rather of the activities. Okay, so we have activities of C here, D, A, and B. Or if we're going to substitute this equation, that will become the concentration of C times the gamma, or the activity coefficient, D times the activity coefficient, so on and so forth. Okay, so that's the idea. Okay, so before we are neglecting this, however, we should know that we should not be doing that at all. Okay, but however, those are good approximation anyway. So yeah, then the next problem will be this. Okay, so we know how to solve for our concentration. How are we going to solve for this bunch of gammas? Okay, how are we going to solve for that? How are we going to solve for the ionic activities? Well, to solve for that, we are going to use anyway, we're going to use the Debye-Hückel equation. So this is the equation that allows us to solve for the value of the activity coefficient as long as you know the charge, the ionic strength, and the ionic size or the hydration size. Okay, those parameters are already given. Okay, so anyway, so in order for us to solve for the gamma, we have to use this Debye-Hückel equation. Okay, this is the more detailed slide. Okay, so to solve for gamma x, or the activity coefficient of the substance, we have to know the charge of the species X, or the charge of your of the ion that you are concerned with, the ionic strength of the solution. We know how to solve for this, and the effective diameter of hydrated ion in nanometers. So it is important for you to take note that the diameter or the ionic size should be in nanometers, because you will encounter different versions of the Debye-Hückel equation depending on the book. However, the only difference is that this one is in nanometers. Some books are in picometers unit. Okay. So as you can see, looking at the Debye-Hückel equation, it seems so intimidating, right? So anyway, we have to thank the scientist or this researcher Kieland. Okay, thank you, Kieland, because this person actually tabulated all the activity coefficients that we need given a certain ionic strength. Okay, so through Kieland, we're not going to use the Debye-Hückel equation anymore as long as the ionic strength is 0.01, 0.05, 0.01, 0.05, and 0.1. Okay, so thank you, Kielan. However, we'll still try to use the Debye-Hückel equation. Okay, so let's try this